Section 5.5, Modeling with Logarithmic Functions. So let's begin by looking at some graphs. We're going to look at the graph of f of x equals e to the x and the graph of gx equals ln of x. And the reason why we're looking at these two graphs is that they are inverse functions of one another. E to the x is just an increasing exponential function. And remember that e is a number, approximately 2.71828 approximately. So, we've got an exponential function with a base around 2.71828 raised to the x. And so this has the same properties of all our other increasing exponential functions. The domain and the range. Domain is all real numbers, and the range is all numbers greater than 0, and it's increasing everywhere. Now, when we look at an inverse function, the domain and the range switch. So notice that when we go to g of x equals ln of x, that its domain is the range of e to the x, and its range is the domain of e to the x. So that's one interesting thing. Just to say another word about the domain, remember this domain is only numbers greater than 0, so you can not put 0 into ln of x, and you can't put negative numbers. So x is not equal to 0, x is not equal to any negative number. Now the output of the function can be 0, and the output of the function can be negative, but the input cannot be. Okay. Also notice that this logarithmic function is increasing at a decreasing rate, and therefore it's concave down. One last thing I want to point out about this is that sometimes people think log functions have an asymptote because it kind of looks like it's sort of sloping off here. It actually, even though it is at a decreasing rate, it still goes up forever. Okay. So notice that the range is positive infinity. This does go up and up and up and up and up. It just goes up very slowly. That's the big difference, is that once you kind of pass this initial rapid growth, then you get really slow growth. Okay. In general, a logarithmic model looks like this: f of x equals a plus b to the b times ln of x. And we can have an increasing log function if b is greater than 0, and we have a decreasing log function if b is less than 0. We'll look at decreasing log functions in a little bit. Those are a little bit weird, but we will first look at increasing log functions. And in fact, let's look at a set of data and talk about identifying what sort of function we have. Okay, so what kind of function is this? How do we decide? Well, one quick thing that you can do is you can enter this data and do a stat plot and just see if there's anything that you can rule out. The slow way to do this is to look at average rates of change and ratios and so forth, and that's fine, but sometimes you're in a hurry. So if you want to quickly you can kind of rule out any non-possibilities, you can do this. So actually, I'm going to pause the video and enter this data. Okay, so as I was saying, I've got my data entered now in the calculator, and I'm going to go to stat plot, turn my stat plot on, and then I'm going to do zoom stat. And with this zoom stat, I can see that this is increasing in concave up. I've got this curve up. So I know this is not linear, and I know it's not logarithmic. So I can rule out these two. And I suspect that this is exponential. To really nail this down, there's a couple of things we could do. We could look at the ratios of these outputs. So in other words, if I divide 76.7 by 34.29 and then divide 171.56 divided by 76.70. If these are the same, and then so on, this divided by this is the same, this divided by this is the same. If all those ratios are the same, then we certainly have an exponential function. Another thing you can do to verify that is you can do the regression and then check the SSE. So I could do this. I could do statcalc expareg and then we can calculate our SSE by doing sum resid squared. And this is actually really good. So you have to know how to read this. So this e to the minus 5, that means this number is actually 0.000058, which is really small. So if the SSE is very small, 0.00058, I think is what it was, that's approximately 0. So that's close enough, I think, for us to say that this is exponential. And as I said, the other thing you can do is look at these ratios. Okay. All right, so I've got some other computations here. We've calculated the growth rate and the continuous growth rate. All right, so let's look at another set of data. And once again, I'll enter this off camera. Okay, so I've got this data entered, and now let's do a... Okay, actually, let me delete that last function, and then we'll do a zoom stat. That's number 9. All right, so this is different, right? So here we're increasing, but it looks like we're concave down. You know, it kind of looks like this, right? So I'm going to rule out linear. But, oh, and also I can rule out exponential, right? So I can rule out linear and exponential. Now, logarithmic seems to be a possibility, right? Because if you remember what our logarithmic function looked like way back here, there it is. It was increasing and concave down. So let's check. Let's do logarithmic regression. And, you know, I know this is the first time we've actually done a log regression, but I think at this point people understand the idea of regression. So if you go down, it's not LINReg, but if you go down and be careful here, there are actually 2 linear regression methods. We only ever use the first one, so don't confuse yourself. Don't use the second one, linreg number 8. We want LNReg, which is number 9, so there's plenty of ways to screw that up, but number 9 is the one we want, and we're going to do L1, L2, vars, y vars, and you know, we can graph it and see kind of visually what it looks like, and that looks pretty good to me. I mean, I think if I was in a hurry, I would say, all right, I'm confident that that's logarithmic, but if you want to be even more confident, we can look at the SSE. And the SSE, I feel like is going to be very small, and it is. So again, this is scientific notation. This is a very small number. If we calculate the average error, which is the square root of the SSE divided by the number of data points, which is 1, 2, 3, 4, 5, our average error is only significant to the 3rd decimal place, and that's actually good. That's since none of our data is, all this data is to the 100th, right? But our average error is 0 up to the 1,000, until you get to the 1,000th place. So that's enough for us to conclude that we do have a logarithmic function. So that's what this slide is talking about. It says average error is not significant to 2 decimal places. So it follows that y is a log function. All right, one more set of data. I'm going to enter this off camera, and we will then talk about it. Okay, so I've entered this data in my calculator, and I'm going to go ahead and graph it. Don't forget to delete this function from the last example, and go to zoom. I think number 9 is, yeah, there we go. So that's zoom stat. All right, so it's a bit, this one's hard to tell. Linear, exponential, logarithmic, I am not really sure. It doesn't really look like it's exponential in the sense that it doesn't really look like it's concave up and increasing, so I'm fairly confident that it's not exponential. But I'm not sure. It could be linear, it could be logarithmic. That one's a little harder to tell. Sorry, going crazy here. Let's check the. So what do you do? Well, there's two approaches here. We could look at the average rates of change, and that will tell us if it's linear or not. Or we could just maybe try the regression and see what happens with our SSE. So it's sort of up to you. Maybe I'll just go ahead and try the logarithmic regression and see what it looks like. Okay, so that actually looks pretty good. That looks like it's pretty much exactly passing through all those points. So, again, if I was in a rush, I would say, all right, I'm going to go with logarithmic. If I'm not in a rush, I'm going to double check and I'm going to look at the SSE. If you compute the SSE of this in the ways that we've done in the previous examples, you will see that it is very small. And the average error is also very small, which means that we are confident in calling this, yes, logarithmic. Okay. Okay, let's look at an example. Oh, actually, I think maybe what I'll do is pick this example up in the next video.